Hello everyone! When designing a PCB with a microcontroller, you may want to use an external quartz resonator. Just following the selection recommendations is not the best option. Sometimes you need to do some measurements and calculations. In this video, we will calculate some quartz resonator parameters using recommendations from ST, which will increase the reliability of your circuit. You may have watched the previous video on electronics development for beginners. A quartz resonator was used to clock the microcontroller, but we needed to make some measurements to determine the reliability of the quartz resonator in our circuit. Let's turn to the datasheet AN2867 from ST. Here it is written that in order to obtain the necessary for the calculations of figures, it is necessary to make measurements with a probe of low capacitance, not more than 1 picofarad. So the next step was to develop a low capacitance probe. The goal was not achieved. The probe turned out to be 7 picofarad. In this video, we will apply the probes obtained from this video on the quartz resonator from this video. But at the same time, we will apply our knowledge of physics. Everything I am telling you today is based on application note 2867 from ST. Here you will find information on selecting and calculating the necessary parameters of a quartz resonator. From the very first pages, we are told that few people know how to properly design oscillators with a quartz resonator, and often the understanding of incorrect operation comes at the moment when the devices are at the stage of production. I understand for this reason ST created this document to help developers to avoid mistakes. To demonstrate a quartz resonator, this equivalent circuit is used. The quartz resonator operates in a circuit called a Pierce oscillator. For further calculations, we need a number of characteristics. Let's open the datasheet for the selected resonator. As we can see from the datasheet on the quartz resonator, few parameters, and most of them we will use. Let's write out the characteristics. Drive level, shunt capacitance. The rest of the characteristics are contained in the name of the selected quartz, such as frequency, load capacitance. I have put these characteristics in a separate file of the test program. Here you can also see the entire calculation algorithm used in this video. The entire calculation algorithm used in this video is also given in AN2867 section 4.2. At step 0, it is suggested to select fundamental mode designed resonator. In the datasheet for our STM32F103, there is a range of frequencies at which the quartz resonator can work. I chose a quartz at 8 MHz. At step 1, it is suggested to check the compatibility of the microcontroller with the selected quartz. The gain margin is determined by the formula gain margin equal GM divide GM crit. GM is the oscillator transconductance specified in the STM32 datasheet. The GM crit is defined as the minimum transconductance required to maintain stable oscillations. GM crit is calculated by this formula. In step 2, the capacitance value of the load capacitors CL1 and CL2 is determined. Pay attention to CS. This value is taken from the documentation and represent the parasitics capacitance of the PCB tracks and microcontroller legs. It is usually in the range of 2 to 7 picofarad. I took 5 picofarad. we skip step 3. And here in step 4 we can see why we developed the low capacitance probes in the first place. Here the ST campaign proposes to calculate the driving level of this circuit by using a probe with a capacitance no greater than 1 picofarad to measure the peak-to-peak voltage on CL1 called CL2 in our circuit. But as we know, we couldn't make a probe with 1 picofarad. So let's use our brain and the theorem of equivalent transformations. Let's replace the load capacitor instead of C2 at 10 picofarad with the capacitor C mesh. C mesh equal C2 minus C probe. C mesh, a new capacitor to be used for measurements with the oscilloscope already connected to the circuit in place of capacitor C2. C probe is the input capacitance of the probe connected to the oscilloscope. We measured it in the video about making low capacitance probes. At 8 MHz it is 7.11 picofarad. The method of measuring the capacitance of the probes is also given in the video on making probes. Links to videos with detailed manufacturing techniques are provided. You can also buy ready-made samples from me on eBay. After calculations, we get a capacitance of 3 picofarad. The circuit with connected probes will look like this. Then you can replace C2 with C mesh and switch on the circuit only with the oscilloscope probe connected. In this case, the changes in the circuit will be within the acceptable values of plus minus 1 picofarad, recommended in AN 2867. The manufacturer recommends such a capacitance for a reason. The point is that including the probe into the circuit changes the value of the load capacitance. So we resoldered the capacitor and on the output with the probe connected, achieved the specified capacitance value with the required accuracy of plus minus 1 picofarad. Let's take some measurements. I connected the probes in the circuit to the capacitor C2. C mesh now. Selected the output of the necessary information in the oscilloscope. Settings are finally got the desired figure. VPP is the peak-to-peak voltage measured at C mesh level of 1.71 volts. Now we only need to perform a few calculations. Substitute the obtained figure into the formula and get the desired drive level of 30 microwatt. Now it is necessary to compare the obtained driving level of the circuit with driving level crystal. 13 microwatt less 300 microwatt. All the shown calculations I also carried out in LibreCalc tables. In our case, the X resistor is not required, because the driving level of the circuit is less than the maximum driving level of the quartz resonator. If this is not the case, in your case, it is necessary to calculate X. The method of selection is given in AN 2867 section 3.5.3, calculating the external resistor. In the Bataron circuit, it was supposed to use R19 as X, but during the design I made a mistake by placing this element on the input side of the oscillator, OSC32 in. It should have been placed on the output side of OSC32 out. This we will definitely fix in the next version of Bataron. In my case, R19 equals 0. The rest of the steps are not necessary. Today we successfully applied the pulsar probes. Now I know that in the scheme Paleonish quartz resonator at 8 MHz works within the permissible limits. In addition, we found an error in the circuit. Unfortunately, because of the error in the design, you cannot limit the driving level of the quartz resonator. As it is written in the documentation, exceeding these characteristics will lead to a decrease in reliability. In our case, there is no need to limit anything. We will surely fix all the defects in the next version on the device. That's all for today. Subscribe to the channel, turn on notification. Goodbye everyone.